and welcome back to our next fabulous session in this conference that is called Second Generation Surveys. So we are going to talk about new projects and new exciting science for the JAST80. The first talk is going to be from Ignacio Trujillo from the IAC. The title is, as you can see, the missing satellites on outskirts of nearby galaxies. So take it away.
Thank you. Can you hear me well? Also the people from outside. Okay, so today I'm gonna sketch basically the proposal, the letter of intent that we have put a few months ago to the sector for a new idea to how to use the DIT in the next 5 years. So this is an idea of a group that I'm representing here, but it's a collaboration between people mostly from the IC, but also from CEFCA, also from the University of Valladolid, and also from the Space Telescope in the United States. So the key problem that we want to address is a problem that it has now almost 90 years of history after Zwicky in the 30s of last century put a name to the problem of the missing mass. So in other words, the dark matter problem. So as you know, the vast majority of the things that we know about dark matter has been always through the use of galaxies as tools. So you can all remember the studies of the movement of galaxies in coma, but also the study of the rotation curve, now the missing satellites, and etc. So what we propose is to continue using the information that galaxies provide, but this time to try and going a bit farther. So we know that dark matter is out there, or at least something that it looks like a dark matter problem. But we would like to make a step forward and to try to constrain the dark matter properties a bit more, and addressing things like what is the ultimate nature of the dark matter, like, for example, is a heavy particle called dark matter particle, is a warm dark matter particle, so it's something intermediate, is another kind of stuff, it self-interacts, so many different possibilities. Here you can see an example of the two of the many proposals for the dark matter particle, the core and the worm, and you can see that the structure of a halo of dark matter around a Milky Way-like galaxy is completely different, just changing the mass of the particle. So the number of substructure around is totally different, and therefore, if you change also the dark matter particle, it could be a completely different thing. So what are the observables that we are going to try using for addressing the nature of the dark matter particle? We are going to use basically three. One is the size of the objects, the size of the galaxies, because depending on the nature of the dark matter, the size would depend on the properties of the dark matter halo, typically with the size being proportional to the size of the dark matter halo. So if we can have measurements of the total mass of the dark matter halo, and we also have measurement of the size of the object, we could start guessing how this could be connected. Now, what is the meaning for us of sizes? So now it's pretty common to use the effective radius, but effective radius is definitely not a good measurement of the size of a galaxy, because the effective radius, for example, of this Milky Way-like galaxy would be just the center where most of the light is. So we are proposing a way of measuring the sizes of the objects that is tightly connected to, at least in simulations of cold dark matter, with the properties of the halo, which is detecting the radius where the star formation drops very quickly. So the kind of truncation features. And to go to explore this kind of truncation features, we really need deep observations. So we would like having very deep images to explore these features in a good sample of galaxies. Also, of course, very much connected to the properties of the dark matter halo is the study of the stellar halo. So measuring all the amount of stars that are around a good sample of galaxies. For example, this is from an old, now 10 years old simulation from Cooper, where you can see the stellar halos of Milky Way-like galaxies. So you can see what typically Sloan sees is only, according to the simulations, only the very central region, But as soon as you cross 30 magnitudes per square second, you should expect observing a huge extension of material around. But that depends, of course, again on the nature of the dark matter. So different dark matter simulations will produce different structure, and measuring the amount of light outside of this would be a good way of testing what is the ultimate nature of the dark matter. Finally, another observable that we would like to explore on our proposal would be the galaxy satellite function. As you know, there is a well-known missing satellites problem, at least in the Milky Way and in M31, connected to the issue that the number of subhalos of dark matter that you expect from simulation is way much more larger than the real number of structures that you detect as satellites around these objects. This could be, so another thing that you could see that as soon as you move to 10 to the 6 solar masses, which is the mass of the heavy globular cluster, let's say, the discrepancy grows incredibly large, incredibly high. So it's a very strong discrepancy. So we would like to explore this problem in many other galaxies, and also as much as possible trying to reach up to 10 to the 6, 10 to the 7 to maximize the statistics and also to test the simulations. So this is what we would like to address. How do we plan to do it? What we would need? Okay, so what we propose is very deep data to try reaching limiting superbrines of the order of 30 magnitudes per square second, and also to use the narrowband filters to get a distant estimation to the very faint galaxy where we cannot make spectroscopy even with the larger cell. So more specifically, what we propose is the following. So now it's taking some time now. So, for example, for exploring the edges, and by edges, I mean this radius, which I was talking before about the star-forming radius of the galaxy, we typically need to reach a stellar mass density of the order of 1 solar masses parsec square. For example, this is an example of a galaxy that is close to M33 in terms of masses, and you can see that you really need things that go up to 30 magnitudes per square second to really catch the outer part of the galaxy. And to do that, we would really need to use G and R very deep, and also so G and R because are the minimum number of filters that you would need to get the stellar mass density profiles from the superbrightness profile in G and R. And also we would like to have access to deep H alpha data, because H alpha would be a very nice complement way of measuring the end of the current star formation. So the combination of broadband filter plus H alpha would give us a very good way of measuring accurately the size of the star forming region. So to explore the stellar halos, obviously again the idea is to go with very deep imaging in broadband filters. And here you have an example of this is another M33-like galaxy. And you can see how the galaxy looks like when you go from Sloan, stripe 82, which is 2 magnitudes deeper, Las Cumbres, which I put this example here because it's a nice example of what T80 can do. This is with 40 hours of T80, sorry, with 40 hours of the 1 meter telescope in not very good conditions. And you can see that some structures start appearing around the object. And then this is with the GTC 4 hours. Okay, so just to confirm that this structure is real. So for satellites, again, we would really like to have very deep imaging, but this time I'm adding another 2 filters, broadband, and also the O3. And the reasons are the following. So very deep imaging so what are the properties that you would expect in terms of photometry? For example, this is already a 10 to the 6 satellite at around 13 megaparsec away distance, and with a central superbrightness of 27 magnitudes per square second. So the current technology, we are capable of detecting these objects. These are extremely faint, so you cannot see this object in Sloan. Okay, so because of the faintness, it's just below the noise. However, these objects are more or less representative of the kind of object that you would expect in the local group. For example, this is from satellites of the local group. You see that the 10 to the 6 object has of the order of 27 magnitudes per square second, But now we can definitely, with the current technology, and if you do it correctly, you can detect this type of object at a 15 megaparsec distance. Okay, so it's potentially possible. Now, H-alpha that we ask it to use it to detect the star forming region is also very useful sometimes because we have some hints that H-alpha could be connected to the emission of galactic cirrus, at least some of them. So if you have deep H-alpha around your galaxy, in principle, you could use that to distinguish between real satellites from potential galactic cirrus at the same spatial resolution, which is key, because otherwise you have to compare with infrared data, but infrared data that have a completely different scale. So you really would like to have a way of tracing the galactic cirrus contamination at a similar space resolution, right? Then, why do we ask for U and I also very deep? Now this time is because for those very faint satellites where we don't have a way of measuring distances, we would really like to have alternative secondary order, let's say, way of estimating distances by using, for example, globular clusters. So here you have the globular clusters of Centaurus A, and basically all, just to show an example. So you can see that the globular cluster normally distribute, if you have U, R, for example, R and Z here, you can see that you can split more or less clearly globular clusters from the distribution of stars in the image. Okay, so you cannot resolve this spatially, but in principle you have way with deep data to separate this. And you have here the luminosity functions in the G, R, and I band of the globular cluster that they detect. So this is in absolute values. This is minus 6.7. So this is minus 7. This is minus 8. So for you to have an idea of what are you trying to find. So for remembering you all, the distant modulus at 20 megaparsec is of the order of 31.5 magnitudes. So you can clearly see that if we make very deep data, in principle, this is this kind of globular cluster, the complete luminosity function of the globular cluster would be potentially possible with deep data in the U, G, R, and I. Now, another alternative way of measuring distances is through O3 line, because in the O3 we can see the planetary nebulae. For example, this is another example of a galaxy observed in O3, and with the continuous, let's say, around the O3 line. And when you subtract it, you can see a way of detections that in principle, according to what we have found in other galaxies, there should be a very quick drop on the brightest planetary nebulae that we can measure. So if we study the photometry of these sources, in principle, we can have a crude estimation also of how far the objects could be. So what would be our observing strategy? Here, so our goal is to go for around 20-25 very nearby galaxies with velocities no larger than 4,000 kilometers a second to avoid the emission lines to go away from our dormant filters. So we ask for declination above 55 degrees. So that implies observing always with 50 degrees over the horizon to have the darkest spot on the sky. Low galactic extinctions, 16 different sky locations, because in many occasions, the targets that we want to explore are within one of the pointings. So that is why we say 16 different sky locations typically to get up to 25 objects. And ideally regions also with ancillary data like GALEX, Spitzer, Euclid, deep H1 data, etc. Here you have a pair of galaxies at 10 megaparsec distance, so you can have an idea of what is the type of target we are trying to observe. So you can see that it's not only the observation of the main galaxies, but also all the satellite structure that they could have around. Filters that we are requesting are, as I said before, U, G, R, I, and the narrowband, and these two narrowband filters that already are in the filter wheel of the T80. The conditions that we request are dark. We don't care much about non-photometric or photometry because we have the J class to make the calibration. And we can work very, very well in conditions up to 1.5 arcseconds. So according to the median, to the distribution of things that you were presenting, it's basically all the time. And by dark, we don't necessarily mean that all the night would be dark. If we can work also on gray nights on the dark half of the night. So in principle, we are requesting 50% of the time conditions because of the dark constraint. And finally, as I said, I think it's obvious to work with photometry based on the J+ because you already have done the work for that. So how do we plan making the 3,000 hours that you are requesting? So as I said, 16 fields, allocating 200 hours per sky field, split on the following way: 30 hours per band in U, G, R, and I, to get this limiting surface brightness with this metric. So here we have made a calculation of what we expect. That according to an object at 10 megaparsec distance, that will imply getting surface brightness fainter than 30 magnitudes per square second, because at that distance, that's equivalent typically of 1.5 kiloparsec, which is quite reasonable for the size of the satellite that we are exploring. And the limiting depth for point-like sources, which is important for, as I said before, globular cluster, identification with the speed of globular clusters and stars. We think, based on our numbers, that we would be able to reach this, which is, I think, is in good agreement also with what you guys have found in J+, but integrating instead of a few minutes, 30 hours, okay? And again, for a 10 megaparsec object, the distance modulus is 30, and as you can see, we would be able to completely explore the globular cluster distribution. In relation to the narrowband filters, we ask for 40 hours per band to reach a limiting magnitude of the order of 25.8 in a diameter of 3 arcseconds, also based on what you guys have shown that we think is reasonable. And that would allow us to detect not only very faint star-forming regions, but also the brightest planetary nebulae up to 15 megaparsecs. And the strategy that we are asking is observations done one galaxy after another to avoid making the observations very long in time. So we would like at least to have one galaxy or two galaxies fully done in a year, and therefore we can immediately start publishing papers and also testing that everything is working under the conditions that we would like to have. In relation to the dithering pattern and data reduction, our observations require a wide dithering pattern. For example, here is a galaxy, and you can see the structure of the pointings we want, typically of the order of the size of the object that we want to explore. So for the galaxies that we are requesting, that would be typically 10 arc-minutes step. Okay, so it's completely within the field of view. So we make most of our time on the source, so we never go far away. But as you can see, we require this, and the reason is because the flat field, the flat field is done with the science images itself. We really need to make the flat field correction using the data to have as flat as possible the data, right? So we would use the CEFCA general reduction pipeline, but if necessary, and this is something that is why it's great to have also people from CEFCA involved in the project. If necessary, we would include specially designed codes, mainly GNU Astro, in collaboration, of course, with the CEFCA IPHAS to get the most from the data. So finally, why using the T80 telescope? Well, I think is the facility for doing this in the Northern Hemisphere. We have, of course, the LSST in the Southern Hemisphere, but it will take 10 years time to get the depth that we are requesting here. So if we can make it already from the north, why not making it? So a fantastic advantage that the T80 has is the large monolithic CCD camera, so 1.4 degree. So remember that other big cameras have smaller CCD units, and that is a nightmare when you want to explore big objects, because as soon as the object is larger than your CCD, you cannot make much. You can mind the complication of trying to get low surface brightness in these conditions. Here, this is not an issue because we have a huge CCD. Then, good spatial resolution. Of course, there are other people with a telescope of the order of 70 centimeters pointing to the sky, but the problem is that they have very wide pixels of the order of 2-3 arcseconds. And this is key because, again, it's not only about the depth of the data. The spatial resolution is key. So look at this. This is a comparison between Dragonfly data and the LBT data. So you here can see that okay, depth is relevant, but also if you want to make detection of globular clusters, correcting by a star or foreground or background objects, you really need to see them. You cannot have objects inside the pixel. Okay, so spatial resolution is key, and also the main advantage of the T80 and in the Javalambre telescope is the narrowband filters, which make a strong difference for exploring science that has not been done yet. So the team, as I have said, is a collaboration of 11 people, open to anyone really willing to exploit the data. So we are fully open to that. The most, the better. And this is the general distribution of the work so far. Of course, very preliminary. We have to discuss it more, but we will have at least 2 people in CESCA working on data supervision. We will have a student coming very soon working on the extended PSF of the data. And other people, experts like Sebastian Comeron working on 6Ds, Mireia on diffuse galaxies, Javier Roman working on globular clusters, etc. So a lot of people with a good expertise. Publication plan, of course, is just a scheme, but by the end of the first year, we would expect having the survey presentation paper with the first galaxy fully done, including the techniques and the limits that we have. In 2024, we expect first papers with more galaxies on galaxy edges, luminosity function of satellites for the number of galaxies we have, galactic cirrus in H-alpha, these 6Ds. And then for 2025 and beyond, with a larger sample, we would expect starting to see the difference on the luminosity function of satellite depending on the galaxy type, the variety of stellar halos, the luminosity function of globular cluster, planetary nebulae, extractal properties of very faint satellites of like the Magellanic Cloud as a strong case for lambda CDM, as David was commenting yesterday, trying to find satellites of satellites, which is absolutely a key test for lambda CDM. Exotic dark galaxies that no one has seen so far. Finally, potential variability of our own data in narrowband emission on top of the galaxy. So for example, do we have reverberation of our own galaxy itself? So that would be a very cool thing to study. Finally, my last slide is legacy value. So we would provide to the community between 20 to 25 nearby galaxies with deep imaging with nearly the LSST depth, plus H-alpha and O3, exquisite data reduction for loss of advanced features, the possibility of plotting variability at the most scale level in 16 different sky positions. So you would have plenty of stars to explore, or point-like sources or high-energy galaxies to explore in this sense. Images releases, we compromise to make images releases with the scatter light field removed. So effectively like having an observation outside of our own galaxy. A catalog of point-like and extended sources. And I think it's very reasonable to consider 3 data releases over the period of time. So the first one 1 year after starting the observations with an example of a galaxy so people can play around. A midterm release 3 years after the starting observation. And finally, once the survey finishes, all the data should be publicly available, because I think that as soon as it becomes public, that will get more pressure on us to make the papers out. Thank you very much.
All right. Any questions for Martin? Nothing. Over there.
I'm curious. You said that you are going to track distances of globular clusters. How confident and what is the way you use to identify the globular clusters? How do you do that?
In principle, as I was saying before, Hector is asking about how we plan to make the estimation of the distance to the faint satellites using globular clusters. So as you can see here, with a combination of 4 filters in broadband imaging, in principle, we would be able to split a globular cluster from a star. Of course, this is something that we can explore in much more detail, also based on JAST data that you have already, and we can explore, so we can even decide which filter combination would be the best. We cannot, so G and R are for us a must, so we have to go with that, because otherwise thermal mass densities right there. And here I didn't put set band, for example. I put I band because set band then it goes drop, so the efficiency goes very quickly down in the red. So and also you saw also the fringing pattern that was complicated. So I think this is the most effective in terms of broadband imaging to get this done.
What I don't understand well is that you try to detect very faint satellites. So it means they are very low luminosity without absolute magnitude, maybe greater than -10.
Yes.
The problem is that this galaxy has now or very few globular clusters. For example, with an annular rate of the local are -10 and we have none.
Exactly.
So how can you
exactly? That's a good point because, as you know, so some doesn't, but some, on the other hand, as you know well, for example, have a lot. For example, these ultra diffuse galaxies are apparently having at least 10, 12, even 20. So that is why I'm proposing at the same time that is globular clusters, but also planetary nebulae. So just to try to find some. And of course, in the end, this is a crude estimation. So if possible, we would also make a photometric redshift. You know, this is it's a very complicated
When
problem.
you talk about ultra diffuse galaxies, you mean that some of these ultra diffuse galaxies are actually satellites, or
Yes,
they are dwarfs.
exactly.
Assume they are not failed galaxies; they are more.
No, they are for sure
galaxies.
satellites. They're for
They
sure
are
satellites.
satellites.
Yeah, they are satellites.
Okay, and in this case, you have more globular clusters. They are very distracted.
Exactly.
Okay.
Tony?
So, I mean, very impressive. I think it's a very interesting, very consistent project. So you mentioned that, of course, you need dark conditions for this
Yes.
project. This is very clear. The sync is not very critical. You said about 1.5 or seconds at the limit. And you also mentioned that having photometric or not photometric nights doesn't really matter because we plan to use J+ data to calibrate that. But have you considered the possibility that because of the large field of view of the instrument, if you are observing in a non-photometric night, it may happen that not only you have a 0 point that changes, but that changes across the field of view. So how this change on atmospheric extinction along the field of view could affect to the
You're talking about the illumination correction that Hector was talking this morning?
No, I'm talking about that you have
extinction, different extinctions.
Like
Okay.
that, so the calibration is not the same for the whole image.
Exactly.
There is some structure that may be artificial.
Okay. And I think here is key again having the all the experience that you guys have, because we don't need to invent the wheel again when you have found that you have differential problems on photometry through the field of view. So in that sense, that is why I was insisting on using as much as possible all your tools. So as once you have the bright stars done, or then you have the photometry of the rest. Yes,
I mean, somebody, some expert here can correct me if I'm wrong, but I don't think we have a fitting surface to compensate for this differential calibration that you have in the same field.
But we can split the field of view into different pieces and make the photometry based on that.
I mean, that would, I understand that would complicate a little bit things.
But I don't think it's so complicated. I mean, it's just a matter of. So
again, thank you for the thought.
Yeah, so Tony Marin was asking what happened when you have different photometrical conditions over the field of view, and how do we plan to manage that? And I was saying that we could split the field of view in smaller areas to make the reduction.
Yeah. I think when you say non-photometric, you mean that the extinction can change along the night, but I think that you are not saying that to have theme.
No.
Okay, because I think I mean sometimes the clouds you don't see them. I mean, yes, I mean, but you when you review the data and you see that you have this kind of behavior that Tony is saying that you actually see strong variation. Let's say high frequency phase variation of the field point. Of course, if you have a variation of the extinction of the night, slightly variation of the extinction with the image. And I understand that this is something that you can live with. I mean, it's just when you say non-photometric, it's non-photometric but clear. Yeah. Okay.
Okay, sorry, but I think we have to move on to the next speaker. If you want to discuss something with Ignacio, if there is any question there, all right, so the second talk will be from David Martínez Delgado, and he will talk us about the legacy JAST80. Sorry for Milky Way star spin. George.
So, hello everybody. So I'm going to present the project about a legacy survey of Milky Way stellar stream with the JAST80 telescopes. In my talk, I'm going to concentrate more in the scientific case and target and our plans because we are still working the survey design. But I think it will be enough for synergies between other groups. But this is our team composed of people with different expertise, some people with a long tradition looking for the stellar stream, the Milky Way, and beyond the local group, but with the participation of the IEA, University of Valencia, University Complutense de Madrid, University of Surrey, the ISC, NOAO, University of Virginia, the CEPCAT, and the INAF. Well, the main question that we want to answer with this project is how the Milky Way formed. But cosmological simulation, both in colder matter and water matter, predict that a galaxy like the Milky Way formed by the accretion of a few hundred of satellites during the Hubble time. In fact, the debris of this process should be detectable in the outskirts of the galaxy nowadays. In this project, we are more interested about what kind of information, what kind of constraints we can get from the stars in the halos. And this is challenging because the stellar halo is only 1% of the mass, stellar mass of the galaxy. So this means that these features are really, really faint. But these are some models too from Bullock and Johnston. For example, this is what we should expect in a stellar halo is a complex structure of debris. In fact, also some survivors. The idea is, first, if we can detect them, and also, what can we constrain about how the Milky Way was built? This process, in fact, go on nowadays. The most spectacular phenomena within this hierarchical galaxy formation scenario are the stellar tidal streams. In fact, one dwarf galaxy is enough to leave a large structure, a very complex structure like a ribbon of the star in the halo of a galaxy like the Milky Way in a few gigayears. What is the?
It's attached to my laptop, not
Okay.
yours. But we can.
The point is the people outside cannot see
The pointer, yeah.
pointer. Okay. Well, at the end of this process, you see that practically this. Sorry.
Because I connected. Okay. Maybe it's very full.
Okay. So I'm going to put the movie again. So as I was telling you, sorry. Too many movies. Okay. At the end of this process, not only the star, also the globular cluster, the matter of the dwarf galaxy are incorporated to the halo of the massive galaxy. But you can see in this movie by Forbes et al. That at the beginning you see a very coherent structure with a morphology depending on the type of orbit, and at the end, due to the dynamical friction, the satellite falls to the center of the galaxy. Oh my God, we have interference now. So at the end of this process, practically you don't see any more current feature, and it's very difficult to distinguish what belongs to the former satellite and what belongs to the in situ halo of the galaxy.
So we are not sharing the screen. Check.
The people outside seeing the presentation.
No, the problem is that the Wi-Fi was disconnected and then you stop sharing the screen automatically. Okay. It's play or play?
Okay.
Man?
Okay, this is a romantic view that we can expect for a stellar stream from inside the Milky Way. So in fact, it's a very long structure that covers practically the full sky and with a very low super brightness. This explains that this is a very young topic, it has only 20 years old. And also it shows us how challenging it is to study this kind of structure from our point of view. You need a very wide field of view and also field of view and also to reach very low super brightness regime. But the first stellar stream was in fact discovered in the Milky Way. It's the famous Sagittarius stellar stream, and it's a stream from a dwarf satellite that is behind the galactic center from our point of view, and is around the projector is around about 25 kiloparsecs from the sun, and we started to look for the stellar stream with the INT in the beginning of this century. In fact, we found several debris, and then of course this is the Martínez et al., Delgado et al., 2001, 2004, and this observation showed that in fact the stream of Sagittarius is wrapping the disk of the Milky Way. Of course, the large scale surveys later show a spectacular view of the stream. Even today, we have data also from Gaia to show also the full stream. So it's a very well-known feature, and it is confirmed that it is the debris of a satellite. In fact, this work in the Milky Way inspired to look for another stellar stream in nearby galaxies, but we use amateur telescope for that. Also surveys using the Canada French Hawaii telescope of the resolved stellar population of the Milky of the Andromeda show also this fossil of the hierarchical galaxy formation. So this observation, in fact, very consistent with the prediction of this cosmological simulation that I showed at the beginning of the talk. So what is the interest of studying Milky Way stream? Well, the main interest is to provide observational constraint in the local group, because in the local group we can study the stream in detail. We can get distance, we can get study the stellar population, kinematics, even proper motion now with Gaia. But to answer several open questions about the galaxy formation theories proposed by the lambda CDM paradigm. First, it's important to constrain the galaxy assembly emerging history of our galaxy, but the main question is how our galaxy was formed, and practically we think it's still forming. So the building up of the Milky Way has not been yet. Also, understanding the disk halo interface, how this process affect the disk of the Milky Way. For example, is the disk the Milky Way transparent on this kind of stream, or they are exciting star formation in the disk. Of course, constrained data models. We can use a stream like natural test of particles to weight the data halo of galaxies like the Milky Way. But this is only possible because you need the dynamical information in our galaxy now. And also get information because you have practically the orbit of the satellite frozen in the space. You can use this to get the shape of the Milky Way potential. That is fundamental to get an interpretation of the full shape of the Milky Way. Right? So, for example, in this project, we are very interested in the star formation history of the stellar stream, because we would like to know what is the contribution, how contribute this, for example, Sagittarius and other major events known now in the Milky Way to the stellar population on the halo, and also what mass of the halo is formed or comes from this minor merger. because we know some part of the halo, the inner halo, was formed in situ from gas accreted from outside, but also we have this external component, this accreted stars. It is unknown now exactly what is the contribution to the halo formation. So starting in the local group, that in fact excellent laboratories to explore the threat, also the orbit, and the tidal interaction star formation history of the accreted satellite. I mean that as you see the orbit and the orbit of the satellite, and you see also the screen in the space, you can disentangle is, for example, you can identify an episode of star formation maybe correlated with pericentric passages or with the tidal orbit of the satellite, right? For example, this is some models that we have done in our team showing all the formation of some of the stellar stream detected beyond the local group. Right? This is some possible scenarios that we would like to understand better with studying the stellar stream, particularly Sagittarius. The first is related with the star formation of in dwarf satellite. First is a string is able to collide with the disk of the host galaxy and produce a complex star formation. This is the scenario to the left. On the contrary, due to the interaction of the satellite with the host galaxy, for example, in the pericentric passages, you can explain episodes of the star formation in the dual satellite that we in fact know they happen in the local group dwarf galaxies. So what is the effect of the orbit in the star formation history of dwarf galaxies? But this is a case that we discovered a few years ago, where we suspected that a string was colliding with the disk and forming a ultraviolet blood, maybe a very strong region of star formation in the disk due to the collision and string. However, our theoretical model cannot explain it. I think the best interpretation could be that we are observing an episode of star formation in the trajectory of the satellite. This is the kind of problem that we would like to address in more detail in the local group, in the Milky Way stellar stream. And of course, as I told you, if you are able to detect outer wraps of the stellar stream in the outskirts of the Milky Way, you can use them as tracers of the matter halo of our galaxy. For example, you can see in this movie, as soon as you are able to get the velocity, you get a good sample of stars in a distance larger than 100 kiloparsec. They are wonderful spectroscopy target to wait and to constrain the shape of the dark halo of our galaxy. So in this movie, you can see as depending on the total mass of the dark halo or the shade of the dark halo, you have a completely different. You see as the distribution of the radial velocity on the orbit change. This means that you can use the stellar stream, especially the outer regions of the stream, the outer wraps, as a test, a natural test particle for that. We know Sagittarius, for example, but from observation from external stream, we are starting to discover outer wraps. They are pretty faint, and they remain undiscovered in our galaxy. So one of the main aim of this project is try to detect these outer wraps, all pieces of Sagittarius that could be a distance larger than 100 kiloparsec. Of course, beyond of the reach of Gaia. Sorry, because the speak with this is like to go to the gym. Okay, I speak too fast, and sometimes I think it's need more training for. Okay, well, we have in fact two targets for this project. One is target one, is obviously Sagittarius stellar stream, is archetype of a stellar stream in our galaxy. It could be also used as testing bed to identify a accreted star in the halo, because one of the aims that we want to undertake with this project is to develop a technique to isolate accreted stars in our halo from not from Sagittarius, from other merger events. And also this the main sum of the objectives first to derive for first time an accurate star formation history of the Sagittarius star string. And for that, we will take advantage of the new filters. Having filters that are sensitive to metallicity will allow to break the generally the color magnitude diagram and to date different episodes of star formation along the string. Then, as we have accurate embodied simulation of this merger event, we can try to constrain with different passages of the string pericenter passages, for example. Also, we hope to identify or to intermediate star in the string for first time, now to know what is the contribution of the intermediate star to the halo. You know that the stellar halo is assumed to be composed only for other stars. So this kind of event of satellites being destroyed in the halo contaminate the halo sample. And we would like to know what is the contribution of the Sagittarius to intermediate population. Also, as Nacho mentioned before, we don't know if Sagittarius was accreted alone. We know now that the larger magnetic cloud has satellites that are coming together with in the local group in the Milky Way. So maybe some overdensities or satellites or globular cluster could remain undiscovered. So one of the main aims of this project is to try to identify overdensities that could be the remnants of globular cluster or former dual companions that were accreted together. And also to search for the outer wraps. This is what I mentioned before. We're very interested to look for Sagittarius string in the outskirts of the Milky Way because they are the best target for spectroscopy for studies of to weigh the dark matter halo. And for this, I think the best traces are blue original brand. So using narrow filter with the T80 allow to do a very strong discrimination to isolate a very good sample of blue original brands at larger distance and to try to identify these wraps. Well, there are some evidence of star formation variation of gradient of the stellar population on the string due to Gaia. So, but they are only from broadband photometry. The main contribution on this paper is to add new G+ photometry to, as I told you, to improve our knowledge about the star formation history along the full string. This is the model by Peñarrubia et al. And you can see it's covered as the string covers the full sky. So we need to look for a survey design to try to trace the full string, to map in different wraps and different regions. Okay, but this is more or less our target field. As you see, the advantage is we can observe any time because the string is visible the full year. We have target during the full year. Okay, and there are some parts that are a bit maybe not too south, but the majority of the string, especially the apocenter, it could be the most interesting region, is well in the north latitude hemisphere. Okay, now also to say that we will use embodied simulation for comparing with our data to interpret our results, but unfortunately, after 20 years of the studying the Sagittarius string, there is not yet a simulation that can reproduce all the observations, even using the recent Gaia data. So the basic explanation is that maybe to assume the Milky Way and Sagittarius alone is too simple. And this is like the paper say a tango for three. You need to include the large magnetic clouds in the simulation to try to explain all the features. And also this is, for example, some result from this kind of simulation. And you can see, for example, this is the projection of the tails of the projection in the space of the tails, the leading tail and the trailing tail of Sagittarius for different shades of the dark matter halo. So you can see the position of the tails of Sagittarius are sensitive to the different shape of the potential of our galaxy. And this is an example of how, when you have data, for example, for one filters that allow to discriminate to constrain metallicity, you can identify narrow features like overdensities, tails, and other things. Well, I think I had not too much time, but I'm going to introduce the second target. The second target was discovered only a few years ago. It's maybe the major that happened in the Milky Way around 10 gigayears ago. And it comes from a satellite that was 10 to the 10 solar masses. It was called the Gaia Enceladus of the SOSIC because it was identified the velocity of space like a SOSIC. So the idea is to try to identify this. The problem is, as I showed you at the beginning of the talk, it's practically dissolved in the halo, so there are no coherent features. However, some models are predicting that the Virgo and Hercules Aquila cloud discovered with the Sloan around 10 years ago could be still coherent features associated with this major event. So one of the scope of our project is to try to first to confirm the common origin of these two clouds by means of the star formation history, mapping this cloud not only in the sky, also in the line of sight. So because this could be the only opportunity to study a tidal debris of this minor merger that happened a long time ago, and it produced a huge impact in the formation of our galaxy. Okay, it's very, very poor known for the moment. But only to say that we already started with some tasks and project preparation. In fact, one of the most important things is that we have the synthetic color magnitude diagrams already in the G+ filter. So with this, we can do synthetic color magnitude diagrams of our target and try to look what is the best combination of filters to isolate a given tracer, or all this is used to try to define our observing strategy. Also, we are thinking that it will be good to modify we need to do this will depend on manpower to modify the pipeline in order to obtain stellar PSL photometry based on maybe better Dalfo 2 and what studying instead of self-destructor, because self-destructor is more for galaxy, but in self-destructor the stars are the garbage, so we would like this garbage. So yeah, so I think Dalfo 2 and all star will provide a better galaxy star separation that is a key for detecting extreme star at larger distance. Well, and we are working now in extreme target field coverage filters. We had a PhD student who is going, I don't know who is around, who is going to start his PhD in this topic, but in this project. Also the filters, I think it's clear that the filter related with metallicity, G395 is the most interesting one. In fact, Juan Miró already did some studies of using synthetic color magnitude diagram to see the sensitivity of the different tracers to the metallicity. And look, for example, you can separate very well the RGB star for different metallicities, and this is still in progress. And I think that's all. So in conclusion, this telescope, the J-80 with a wide field camera and this unprecedented net set of narrow filter, I think it's a unique opportunity to study the Sagittarius tidal string and the Euclid Gaia string in detail to constrain their origin and the stellar population. And of course, one of the main legacy of this project will be a bona fide sample of a reflecting star with a strong synergy for the future coming for spectroscopy surveys. For example, you can see DESI, Formos, WIG. So that's all. Sorry for some problems during my talk, and I hope I can answer your question. Thank you very much.
Thank you, David. We have time for one quick question.
Okay.
All right. I think, Sylvia, could you unmute yourself and just speak?
Yeah, hello, can you hear me?
Yeah, we can hear you.
Yeah, very loud.
Okay, sorry. Hi, thanks for the talk. It's very interesting. I was wondering though, if you could expand a bit more on the survey strategy. Maybe I lost you for a couple of, a few seconds here and there because of the connection. So I'm not sure, maybe you mentioned it more in details and I missed it. What would be the strategy of observations? Where are these fields and how they complement with JPAS, for example?
I'm not sure. As I told you, the main scope of this talk was to introduce the scientific case and the motivation of our project. But of course, what we are trying to do is color magnitude diagrams along the streams, okay, and compare this with synthetic color magnitude diagrams, and also to use color diagrams that we will in order to isolate different samples like blue horizontal band RGB stars. And also, we are also very interested in separated giant from dwarfs from the thin disk of the Milky Way. So we are now looking at the synthetic color magnitude diagram to check what are the best combination to try to undertake all these scopes. I'm not sure if this answered your question.
Yeah, I mean, I guess I was a bit more curious about the general things, like what is the area that you expect to cover, and you know, how many hours that would take, and so on.
We don't know this yet. This is something we're still working, because we need to first, we are going to take synthetic color magnitude diagrams to check what is the limited magnitude that we need to reach, and then take account that the main problem is that the distance of Sagittarius change along the sky. So you cannot use the same exposure time for each field. In fact, you have a range of between 20 kiloparsecs to 60 kiloparsecs. So the exposure time is changing. So the survey strategy is difficult. And I think I prefer to, I hope to, no, I will include this all in the proposal, of course.
Okay, thanks.
Right, let's thank our speaker again. So the last speaker of this session is Jorge Casares, and he is going to talk about mini holes, a pilot survey to unveil the dormant black holes. Jorge, the floor is yours.
Thank you. Hello, everyone. Well, I'm going to present mini hoax. It's a pilot survey, it's a test of a new observing strategy, which hopefully will be able to will lead us to unveil the hidden population of these galactic black holes. But I would like to start with a little bit of introduction and also talk a little bit about the motivation of the project. Well, you see there my name only, but by no means it means that I am the only person working on this topic. We have the umbrella of all the X-ray binary group at the IAC, which consists of 4 postdocs and 4 PhD students, and 2 of them in particular, Manuel Torres and Idaira Llanes, will be fully dedicated to the handling of the data and the analysis. So let me start with the basics. Most of the black holes that we know in the galaxy have been discovered through X-ray outbursts. So they are part of a subgroup of systems, X-ray binaries, that they are called transients. So the main property is that they exhibit X-ray outbursts, dramatic X-ray outbursts, caused by viscous instabilities in the accretion disk around the compact object. And when these outbursts are triggered, these systems are the brightest X-ray sources in the sky. They are very easily spotted by X-ray satellites. And the key thing is that after a long decay, they settle down in a quiescent state. And there we have a unique opportunity to detect the faint companion star and then perform dynamical studies, measure the radial velocity curve of the faint companion star, and then constrain the nature of the compact object. Well, after 50 years of intensive scrutiny of the X-ray sky, we have been able to discover just under 70 X-ray transients. So this is a cumulative histogram of the history of X-ray discoveries. And these systems, they are strong black hole candidates, but unfortunately, only a third of these systems have been confirmed as real black hole systems. And why is that? This is simply because when they go into quiescence, they are too faint even for the biggest telescopes. Dynamical studies that will eventually prove that these are black holes, they cannot be performed. Basically, we are scratching the surface of a large population, which is estimated in about a few thousand dormant black holes in the galaxy, from which we know nothing about. And I mean, this is striking to realize that at this pace, it would take actually 200 years in order to increase the number of dynamical black holes by an order of magnitude. So why bother discovering more black holes in the galaxy? Well, to start, this is important actually to learn about X-ray binary evolution and black hole formation mechanisms. To start with, we don't know yet how these systems have formed. We don't know how the companion star has possibly survived two things. First, a common envelope phase, and also a supernova explosion that could disrupt the system. So if you take the standard evolutionary models, we would predict that there would be only 10 such systems in the galaxy. But on the other hand, if you extrapolate from the number of discoveries, we expect a few thousand of dormant black holes in the galaxy. And also, it's very important to build the mass distribution of these objects, because this encodes information about black hole formation processes. Take, for instance, the classic diagram, the LIGO-Virgo diagram, and then you can compare here the masses of the galactic black holes in purple to those of gravitational wave discoveries and the neutron stars in the galaxy. So then there is a hint of a mass gap between neutron stars and black holes, and there's also some evidence of a mass cap for galactic black holes at around 15 solar masses. So there are important questions to be solved. So is this mass gap actually real? Is telling us something about the supernova mechanisms, or is observational bias, because we have such a small number of systems? And also another important question to answer is again this mass cap an observational bias, or really black holes in X-ray binaries at solar metallicity are formed in the range of the black hole masses measured by LIGO, but for some reason they are concealed and we are not seeing them. So in order to be able to answer these questions, these fundamental questions, we really need urgently to increase the statistics by an order of magnitude. Now, problem is, how can we increase the number of black hole discoveries? Well, this is a very difficult problem, because by their very nature, these quiescent black holes are very weak at X-rays, but also at UV and radio frequencies. However, if we look at the optical, then the energy is basically the spectrum is totally dominated by the companion star, which typically is a late K star. But the key feature is that this spectrum has superimposed broad emission lines, double peak emission lines, that they're coming from the accretion disk around the compact object. So in principle, H-alpha surveys that have been performed before, like GBS or IPHAS, might contain some of these black holes, hidden black holes in the galaxy. But the problem is that these are largely outnumbered by other populations of H-alpha emitting sources in the galaxy, like theta stars, variables, that they are much more abundant. And the reality is that not a single black hole has been discovered or has been produced by these parameters. So there is an open window of opportunity that has been created by the discovery of a correlation between the velocity amplitude of the companion star and the full width maximum of the H-alpha line that is coming from the accretion disk. So this correlation is very tight and is telling us that there is a fundamental scale in the dynamics of the gas from the accretion disk and the companion star. And this is important because this means that we can weigh black holes simply by resolving the width of the very strong H-alpha line, rather than measuring the very weak, the Doppler motion of the very weak absorption lines, which eventually will lead us to the velocity, the measurement of the velocity amplitude of the companion. And so in order to weight the black holes, what we need to do is basically combine the velocity given by the scaling, by the width of the H-alpha line, with information on the orbital period that can be provided, for instance, through time variability, through orbital light curves. And so you combine this in the well-known mass function, and this gives you a lower limit to the mass of the invisible star. So basically, this correlation is offering us a new way to detect black holes through exploiting the width of the H-alpha line as a proxy of the very strong gravitational fields that are typical of black holes. But really, the key, let's say, breakthrough in this technique would be to apply photometric techniques, because these are much more efficient than spectroscopic techniques. This will allow us to perform blind black hole searches over large regions of the sky, and in order to detect stars with very broad H-alpha lines. And so this actually is the inspiration of a survey which is called, I have named HAWKS, which after H-alpha width kilodegree survey. So you need to survey kilodegrees in order to be able to discover a substantial population of these objects. And as I said before, this is much more efficient than doing searches through classic spectroscopy or fiber spectroscopy. So I estimated that you need to do a survey of about 3,000 square degrees down to 21st magnitude in the galactic plane, that's where all these objects are, or 90% of these objects are concentrated, in order to discover about 150 new black holes. That would be a tenfold increase over the known population. But this is a massive effort. So now, for the time being, what I'm proposing is to do a pathfinder, which I call mini HAWKS, will target a small region of the galactic plane, 50 square degrees, in order to test the observing strategy of HAWKS, and also to measure or estimate the discovery rate of black holes. In such area, we expect like 2 or 3 black holes to be discovered, which is already a 10% increase over the known population. And so we have how to measure photometrically these H-alpha widths. We've been exploring this, investigating this problem in the past few years, and basically, we published the results in a couple of papers. In the first one, we present a proof of concept of the technique. Basically, what you need is 3 H-alpha filters. The 3 of them must be centered at the rest wavelength of H-alpha, and they must have increasing widths in order to cover the core of the double peak emission line, the entire flux of the line, and an even broader filter to cover the adjacent continuum. Then, well, I make simulations of synthetic double peak emission lines for a range of widths and a range of equivalent widths, I mean intensities over the continuum. And then I prove that combining the fluxes that you obtain after convolving these lines with these filters, then using some basic equations, simple equations, then you can recover the what I call the photometric width of these lines. And then we compare them here with the input model widths, and then you can see that one can reach a very nice recovery, no matter what the equivalent width of the line is. And in a second paper, which I summarize on the right, we applied the same technique using actual data, actual observations, but instead of the ideal filters, we used a set of practical filters that they were available at the Observatory of Los Muchachos, and then we basically demonstrated that we can recover. I mean, we did this with simultaneous spectroscopy. And then we demonstrated that we can recover photometrically the width of the H-alpha lines to within a 10% for systems which are down to 20 second magnitude. So in a nutshell, these three filters define a new photometric system, which is especially tailored to measure the width of the line, but not only width, also the equivalent width of the line, which is important. And here I show you a couple of synthetic diagrams that I have made based on the Gaia galaxy model for two particular fields of 1 square degree down to magnitude 22 in R, and pointing towards two different directions in the near the galactic plane. And these are directions which contain two black holes, two dynamical black holes. And this, what you can see here is a diagram of a color diagram based on these filters. This is a very practical way of presenting the information that the filters are providing. Also, you can see that, for instance, let's take the left one diagram, and this diagram contains over 100,000 field stars. But all these stars are concentrated here, in this part of the diagram, near basically the focus of all these lines. So they don't mix with the other populations of H-alpha emitting stars. And so it's interesting to realize that this diagram provides a unique determination of the equivalent width and the width of the line for each object. And also, it's important to note that this diagram is not sensitive to the extinction, to interstellar extinction. This is why all these the 100,000 field stars, they cluster over here. And in order to guide the line, the eye, I have plotted in horizontal. These are lines of constant equivalent width from 10 to up to 400 angstroms, and the curved lines, they represent lines of equal full width maximum, equal width. So then we can look at different populations of H-alpha emitting stars that one expects to find in the galaxy. Most of these stars will be B stars or P Tauri stars, the ones plotted in blue. And you can see that they all have widths which are narrower than 1,000 kilometers per second. Then you get some symbiotic stars. No? Symbiotics, they have also very narrow lines, but they have equivalent widths which are much larger. And but again, the widths of these lines, they are under 1,000 kilometers per second. Only cataclysmic variables, which are the points here marked in red, they can have broader H-alpha lines because of the strong gravitational fields of the white dwarfs, of the ecliptic white dwarfs. But then we can actually find a cutoff. I made some Monte Carlo simulations that showed that if we do a cutoff of 2,200 kilometers per second, then you will be filtering out 99% of all the cataclysmic variables, and then you will still retain 50% of the expected black holes that you can find. And then you have the problem of the flare stars. Flare stars, they are very common, and the initial lines are very narrow, but because they have broad molecular bands either side of the H-alpha line, they can mimic, they can fake actually black holes with very broad, extremely broad H-alpha lines. No? But these lines are not a trouble because we can identify them easily. They are nearby objects, or through Gaia parallaxes and also through very bright colors. They are very easily located. And last thing I would like to say about this diagram is that because the filters are also sensitive to surface gravity effects, so you can distinguish white dwarfs from A stars or B stars. So then you have these points here are white dwarfs. So this diagram that can be produced by the filters is a very nice way of separating the different populations of H-alpha emitting objects in the galaxy, and also a way to identify black holes much more efficiently than classic H-alpha surveys. Now comes now the proposal. Obviously, JAST80 is the ideal infrastructure to perform this survey. I estimated that you need like 14 hours of integration in order to reach signature threshold 50 for in the 3 filters, and but this signature noise is required in order to be able to measure the width of the line with a 10% accuracy. And these observations will be practically performed in a through continuous cycles. I estimated that 40 cycles are needed in order to reach this signal to noise. So basically, you will need like a couple of nights per pointing per field, because we need. I mean, I am proposing to observe a small patch of 50 square degrees, so you need 50 nights, or 350 hours. And you get the bonus of a light curve. You will get 14-hour light curves, which will be perfect in order to identify variable stars, and also in particular eclipsing cataclysmic variables, which are the main outliers for the black holes. For cataclysmic variable, in order to be able to mimic very broad H-alpha lines, it has to be a short orbital period cataclysmic variable, and the system has to be seen H-point in order to see the maximum velocity and the maximum dispersion. So this will be eclipsing. The main outliers for the black hole will be eclipsing cataclysmic variable, and they will be really identified through the light from information. And so I expect that 300 hours are needed to complete the survey. This survey will deliver between 2 and 3 black holes, will allow us to measure what is the discovery rate for hoax. But not only that, it will provide hundreds of cataclysmic variables, about thousands of B stars and other types of H-alpha emitting objects in the galaxy, like Nebulae, which will be of interest to the community, to the galactic community. And let me finish with the conclusions. So I have presented mini hoax. It's a pathfinder of a much larger survey called hoax. So it will test the observation strategy of hoax, and it will deliver about, as I said, 2-3 black holes, but a very large number of other H-alpha emitting objects in the galaxy. So this will make a unique legacy survey, which complement nicely J+ and J-IPHAS, because we are pointing at the galactic plane and not higher galactic latitudes. This will imply some technical development. We have to manufacture these 3 special filters, but we have made some pilot filters, small format filters for faster cameras in ultracam and hypercam by the company Asahi, and we think this is not a risk for the project. And eventually, hoax will allow us to unveil 150 new black holes following this strategy, which is something that will require 200 years. We'll wait for them to go into others. Thank you very much for your attention.
Questions?
Okay. So many questions, but if you expect 2 or 3 objects, you could be in an unlucky situation where you will find anything, because the statistic is very, very small. So my first question is, how much that worries you? So the issue that you try to get this started by the number of targets that you spend is very small. So within the
well, this will be, well, the question is asking is if I'm worried about the possibility that the result of mini hoax is a non-detection of a black hole because the expected number is so low. Well, I would say that this is also meaningful. No? If you don't detect any, then this makes you to revise the numbers that, of the expected population. It sets a strong constraints on the population I have assumed is about 5,000 black holes isotropically distributed through the galaxy, and so the non-detection will put a strong constraints on the size of the total population. That's to start with, and also in any case you get the bonus of all these hundreds and thousands of other H-alpha emitters that will be of interest to the community.
And my second question related to science. So one of the candidates for that matter is an intermediate black hole population. So I was wondering whether you have considered also as a potential target of your science, for example,
imagine that we have a free-floating primordial black hole there with 10, 40 solar masses. Some of them have accreted accretion disk. So, would your techniques able to detect, let's say, objects with an accretion disk that is slightly higher, maybe 10,000 times the equivalent to that, or your technique is only limited to, let's say, a few solar masses?
Well, the second question is whether this technique is sensitive to detect the presence of an intermediate mass black holes wandering in the galaxy. Well, I will be targeting the galactic plane. So first, this object should be in the galactic plane in order to be detected by the technique. And also, well, it will be sensitive to that as long as this intermediate mass black hole is accreting, has an accretion disk, because this is the main. And but then in that case, I would expect that it would have been detected already by X-rays, because you have a massive black hole accreting. Well, it could be in a quiescent state as the other ones.
It doesn't necessarily have companions. So
Yeah, but accreting from the interstellar medium, no?
Exactly.
But you need this black hole to have a accretion disk in order to be detected by this technique. But yeah, I mean, what is interesting that one of the I would say the big questions in the field is why we are not discovering black holes more massive than 15 solar masses in these X-ray planets. No? And there are groups that have proposed that there should be these more massive black holes, with masses of about several tens of solar masses, I mean 20, 30, 50, but they are actually, because the black hole receives a kick during the formation, and well, if the black hole is more massive, then the kick is small, and this is might actually be there, but lying in the galactic plane, and will be concealed by the interstellar extinction. So,
Javier, question?
Yeah, thank you, Jorge, for the next talk. My question is related with the first question from Nacho, but in another perspective. You mentioned in your talk that actually these objects, these black holes, should have been detected or could be, let's say, lost in these H-alpha surveys like IPHAS and similar, right? I wonder if these surveys would provide you some hints or clues. I mean, if I understand well, these black holes would have been detected, but because of the fact that they are only using one filter, they may not be classified as black holes. Is that correct? What I mean is,
yes.
Do you plan to use these surveys to see if you can see some potential candidates that probably do not match other H-alpha emitting sources, to really go to the areas in the sky which we can assume to have the highest probability to find these black holes?
Yeah, okay. This is a Javier is asking if I could use IPHAS to detect or to identify black holes, that potential black holes that they have H-alpha emission, but they have been missed by the analysis of these surveys, basically. Well, the problem, and I think this is a good asset of my survey, is the fact that we are not degenerate with interstellar extinction. So we can measure the width of the line and the equivalent width uniquely. Whereas in the other surveys, in IPHAS, for instance, you've got 3 filters. You have an H-alpha filter, but you've got also an R-band and I-band filters, which have the 3 of them. They have different wavelengths. So this is a typical diagram that you would measure with IPHAS. And then what you see here is in the x-axis is an R minus I color, and here is R minus H-alpha. Basically, the vertical axis is giving you the information about H-alpha excess objects. And this line here shows the main sequence, the locus of the main sequence. So all the objects there should the main sequence which have no H-alpha emission. So what you would expect to find is an object somewhere there which clearly has an H-alpha excess. The problem is extinction. Extinction. This is the reddening line, spreads the objects around along the r minus I axis. And for instance, if you take an object, here you have the main sequence without reddening, and then in the blue you have the main sequence with EB minus V, I think is 1 there, and in red the main sequence for EB minus V 2. No, I think it's there. It says there. So then let's take an object which has an equivalent width of 40 angstroms, but is not distinguished. So the object will be here, will be clearly above the locus of the main sequence of the unextinct, non-extinct main sequence. But if these objects, if you apply a reddening of EB 2, then this object comes into the reddening line, into the main locus, into the position of the main sequence, on reddening main sequence. So then you have this degeneration. You don't know this object is actually a main sequence star, is an as I said here, an early M star with no H-alpha emission, or is actually a reddened object with H-alpha emission. And so this is the problem of the IPHAS filter. So it's very difficult to use information that this filter provides. Whereas in the asset of my survey, or the survey I'm proposing, is that because the three filters are centered at the same line, basically the information is not sensitive to the interstellar reddening or the SED of the objects.
The last question was in the internet, probably?
I think this was one, but
it's gone? Okay, maybe it was answered.
we can
All right. Yeah, so any more questions? The last one?
do you expect any special photometry methods, like what they were suggesting on DAO part, or is something that people try finding out, or special methods for photometry on those magnets with really dense?
Yes, yeah, that's a good point, because there will be.
Oh yeah, please repeat the question.
The question was because I'm targeting the galactic plane, which photometric extraction techniques are expected to use. And yeah, I mean, this is an issue, especially if you are looking at very crowded regions. No? And yeah, so in principle, we're investigating the problem. I am actually involved in one of the commissions of the LSST photometric group that is working with crowded field photometry. And so they are trying differential imaging. Is a good way of obtaining photometric measurements in the very crowded fields, but also PSF photometry. And apparently PSF photometry is doing a very good job. But yeah, I mean, it's something that to consider, especially before deciding the footprint for the. So probably we would avoid exactly the galactic plane when the overdensity is very large, and then we probably move up maybe to galactic latitudes of 2 degrees, 3 degrees, in order to avoid to have severe problems with crowding. Yeah, but in principle, PSF photometry and the differential imaging, we believe they could do a good job.
So I think it's now time for coffee. Let's thank Jorge again and all the speakers. See you back here like in 30 minutes or what?
Can you hear me now online? Okay.
Yes.
Yes.
Thank you. Sorry.
Okay, so here we go again.
So I was saying that we would like to understand the feedback of stars. One of them is by continuous stellar wind at different stages in the stellar evolution. Here I'm showing one arc-like extended nebulae around BE supergiant star. We also know that there are nebulae around OB massive stars, and so they are ejecting through those stellar winds their material into the interstellar medium, and they are also interacting with this interstellar medium and creating bubbles where those stars are going to go later on. There is another example, so those are the so-called Wolf-Rayet bubbles. Wolf-Rayet are the descendant of the most massive stars before they are going to produce a supernova explosion, and they have the most powerful star. In this case, the surface of the star is already enriched in carbon, nitrogen, oxygen, and heavy elements that they are going to be deposited in the stellar medium. This is the so-called Thorne's-Hermit nebulae. We have the much smaller but more numerous planetary nebulae in the galaxy, and those they are going also to eject their envelopes of those low and intermediate mass stars to different processes of mass losses at different states. Mostly, if we forget about the supergiant phase, then we have the asymptotic giant branch phase, where they are going to suffer thermal pulses, and at the very end, they're going to eject all the envelope, so to get just the core of the star, which is going to photonize the. So in these cases, those are very similar to the Wolf-Rayet bubbles, but they are more numerous and they are much more smaller in size. So those are, this is the feedback by stellar wind, but we also have explosions that they are going to inject material highly processed into the interstellar medium at very high speed. We have the supernova that they are going to produce supernova remnants with sizes of many parsecs that they are going to inject a lot of material with iron and very heavy elements into the interstellar medium. And also we have the nova shells that they are resulting for the explosion of nova. In those cases, we may also have recurrent nova, and they have much larger number, and so they are still producing very delicate elements like lithium and other elements that they are not produced anywhere in the universe. So this is like a different number of objects that can inject this material into the stellar medium. Most of the observation of those nebulae has been done either through very shallow wide field H-alpha surveys or very deep observation of just a few individual objects. We don't have a coherent view of how this the mass, the material, and the energy is deposited into the stellar medium. Also, if we look at the flux calibration of the images, particularly for those made with a very narrow filter, it's very difficult to make a flux calibration. And this is something that if we were using one of the H-alpha filters using IPHAS or J-ALFIN, because it's a flat top filter, we can make a very nice calibration. So we are proposing here to make images of a number of those sources, because in some cases the nebulae around them are huge in size. So this is one of the cases. After my talk, Michaela Kraus are going to explain in detail the cases of the nebulae around the supergiants. Here we have one source that is detected in the infrared observation. This is one arc. The size of this image is around 1 by 1 degree, so it's huge shell. And when you try to go deep in H-alpha images, you see also this. So those stars somehow they are depositing large amount of mass into the interstellar medium. We can also look at the Wolf-Rayet bubbles. Those are large cavities into the interstellar medium. This is the Sharper's 308 source. Here is the Wolf-Rayet star, and we have this shell that has a size of 40 meters in diameter. In some cases, it's difficult to know what part of the material that we see here correspond to the circumstellar medium, so has been ejected by the water in the star or by previous phases of the stellar evolution, and what's the interstellar medium. One of the collaborators in this work made an analysis of infrared images, and we realized that we could distinguish by looking at the infrared what's the material from the interstellar medium or from the world radiator. But also, if you look at different emission lines, like in this case where we have the O3 in blue and H-alpha in this reddish color, we can see that here is the nebula, which is really associated. And in this case, the role of Sagna material astronomer using a small telescope and a large number of hours of observation has been critical. Then we have the halos around planetary. So we know this is the Cat-side nebulae, but when we look in very deep detail, we see that this is surrounded by a halo of material that contains a large amount of the mass that was ejected in the very last thermal pulse during the age of phase. So we need to understand what's the amount of the mass and how the PN is going to be evolving inside this halo that has already blown away the stellar medium around the planetary nebulae. In some cases, we are trying to find objects, planetary nebula, that are large and close to us, and so their surface brightness is very, very small. So in those cases, also this kind of instrument that is JAST80 providing is the only one that can provide this kind of observation. This is PUVE1, and this is an image in H-alpha, nitrogen 2, and O3. And you see that also, if we look at supernova remnants, in the very late phase of their expansion, they extend over large areas on the sky. Sometimes we just see one filament, but when we make a coherent view of the supernova remnant, we see that this is impressive nebula. But we need to understand how in those very late phases of the material is emitting it's going to help the interstellar medium to enrich material. Nova shells, well, they are smaller than supernova. We have learned in that recent paper published that they disperse, they basically move ballistically during all their life, and they are going to disperse in the interstellar medium in maybe one couple of 100 years. But in some cases, we see that there are some recurrence in those explosions. And that may be one of the cases. This is one that we discovered in IPHAS. And if we look at the interstellar medium around this nebula, we see some arcs here, and maybe they are so that may be associated to previous episodes of nova explosion. So that's something that is very interesting to investigate using a large field of view telescope. So we are proposing in this survey a deep imaging of a selected sample of ascended nebulae around those evolved stars in a number of JAST filters that they are going to cover key emission lines. With this observation, we are going to be able to provide an information of the excitation and origin of this circumstellar medium around those stars. We are going also to measure the spatial scale of the diffusion. So how far the material reach from those stars until it gets really distributed into the interstellar medium. If we measure the H-alpha emission, probably the emission that we detect is going to be contaminated by nitrogen emission. But using follow-up observation, spectroscopic observation, we can determine what's the level of H-alpha emission and determine the nitrogen 2 plus the density and the distance. Then we are going to know what's the yield just into the interstellar medium. With information on the velocity, then we are going to be able to know the time scale and the energy of the injection, and also investigate the interactions with the interstellar medium. So basically, we are going to be able to assess the amount of energy of material that those stars are really putting into the interstellar medium. And by looking at a sample of different sources, then we can provide to the theoretician and to people studying the galactic chemical evolution what are really the yields and the extended spatial scale of those yields. So our sample is basically consisting of about 100 extended nebulae, of which 10 are going to be nebulae around B supergiants. We have here some nebulae around OB stars, main sequence stars, some Wolf-Rayet jet bubbles, PN with halos, 30 extended late PN. I have back in a different color to remind me that of all those sources that are going to be in the galactic plane, those are the ones that probably are not going to be the direction of the galactic plane. They are in the galactic plane, but they are close to us, so the line of sight actually points out of the galactic plane. For the selection of this sample, we're going to be using our knowledge on the HASH, the Hong Kong AAO Strasbourg H-ALFIN database, which has been developed by one of the co-eyes of this survey. It's basically a database that includes observation of 3,000 planetary nebulae and galactic nebulae with different classifications, and also infrared surveys to select objects when we see those arcs that we see in the infrared that are not basically seen in a H-alpha service. For each of these objects, we're going to obtain different images on different filters depending on the nature of the sources. But basically, we're going to be investigating the O2 emission lines in the blue or ultraviolet, the O3 emission lines, H-alpha, nitrogen 2, and sulfur 2. Typical exposure times are going to be like 2 to 4 hours per filter. We have made some tests already using exposure times up to 10 minutes, which is the maximum that the PSF is preserved. And the total exposure time per target is going to be about 10 minutes. So that makes a total of 1,000 hours approximately, which can be divided by 200 per year. Now we have already obtained some results looking at the J-PLAS DR2 data release. So those are images of some, no, sorry, J-PLAS. So those are images of some planetary nebulae that we see here. In this case, the cat side, we have been able to recover the halo around this source. The Lina Nebula, it has 2 halos. We can see one here and the other is very faint there. And even in this case, this is one object that was observed in this survey. It wasn't known it has a halo, but we were able to see some extended emission there. So because we are interested in knowing how deep we can go with this survey, we made a MIT proposal to investigate the Dumbbell Nebula, which is a well-known source with a halo. So this is the observation that we obtain where we see the typical emission from the Dumbbell, this region here, and then we see the halo. And we can see even better here in this image, combining different filters, where we see the red halo, which is H-alpha and 2 emission. We see the G filter, which is basically tracing in this case here, and there are all 3 emission, and also U, which is tracing the emission from the star. Okay, just to finish, you know that we have a large team that have a large experience working on this kind of observations. And here I'm splitting the different tasks by different members of the group. Michaela Kraus and Tina Limets are experts in nebulae around the stars. As for the Wolf-Rayet jet bubble, Jesus Toala and myself, which we work topic. PN, we have the collaboration of 2 different groups, the HASH group, led by Quentin Parker, and the GRNS group, which is a group that we have developed in Mexico with a number of students and professors and doctors there. And this is going to be led by me. For the supernova remnants, we have the experience by Quentin and Laurence. For nova shells, Gerardo and Ivan Santamaria, and also Tina. And I'd like to emphasize the collaboration that we kept with some amateur astronomers. They are very used to observing for a large number of hours with a small. So they can provide us with some of their expertise on how to combine images and getting the most from the data. Now I can take a question for you. Thank you.
Any questions? Yes,
The type of science that you would like to do is kind of similar to what I was presenting. Very faint in right. I was wondering whether you also, because by looking at your images, apparently you are not, going as much as the data can show you, but you are just showing that. So you are going very deep, but you are not pushing the data, let's say. So I wonder whether you have considered also the possibility of maybe a special dithering pattern, make fields using the data itself, because that has shown us that you can go like one or two magnitude people that just the regular finite path. So by the amount of time that you're requesting, I think that you can go one or two magnitude people with a proper reduction.
Okay, so Ignacio is making a very nice list. So Ignacio is making a very nice suggestion of applying some kind of different techniques so that we can make the flat with the same images, and in this way getting deeper with the observation. This is actually a very nice suggestion that actually I learned this morning when Carlos was suggesting that to apply large different. In many of the cases, I would say that our objects are going to be large, but not that large enough so that we can make a difference having the objects always on the field of view. And this is going to using the same, using the whole amount of time that we are requesting for this object, it's going to improve the quality of the images. In some other cases, we may need to apply some tile technique where a fraction of the time is going to be lost because they're just going a bit off from the object. But this is actually something that I would like to develop. With the DDT that we had on the dumbbell nebula, I realized that actually the typical differing pattern was too small, and that having a larger differing is going to help the cosmetic. And now I learned that also the depth of the cell.
So I don't know how big you are going with this data. I don't know what you're doing with super prime, but with so you said that you are spending like 1 hour in the keyboard.
No, so basically we're going to be using narrow filters. So in this case, I wonder, so maybe I need to ask the experts here from FEFCA, whether the level of the emission on those narrow filters is going to be enough for like a flat field into the same images. I know with that for broadband filter you can do that. That's questionable as for narrow filters. So yeah, indeed, we intend to have like 2 to 4 hours, right? 2 to 4 hour integration per field with 10 minutes exposure per field. So that's a large amount of object, and basically having a good different strategy there. I would definitely know that this is going to improve the cosmetics, but definitely we can go deeper. Now, I cannot at this moment make an assessment of our problem.
Any further questions? Please.
No.
But we could go on the Nova shells parameters. So I will skip the Nova shells. I wonder about the contamination of the nitrogens to the H-ALFIN. Would it be possible using the fluxes in the other filters to model how much H-alpha emission you're expecting somehow?
Okay, so Alessandro, Alessandro is asking whether we can somehow assess what's the contribution of the nitrogen to the H-alpha emission in that filter using different observation in other filters like I would suggest like broadband filters or maybe the oxygen 2. That's difficult because oxygen 2 is going to be very dependent with the extinction and also the chemical abundances of the source, the nitrogen to oxygen ratio. And as for oxygen 3, in many cases, you see that oxygen 3 is very similar to H-alpha. And actually, when you make a ratio between the H-alpha plus nitrogen 2 and oxygen 3 images, if there are small scale low ionization features in the images, they are going to show up in the image. So that's something that which is going to be a part of the analysis that we are going to do for the excitation of the sources. As for the ratio between the nitrogen 2 and H-alpha, I know that there are several papers conducted here also in CEFCA that they're making an assessment of what's the contribution. My experience for planetary needle is that this is very difficult because those objects could be very different one from another. So I would think that we don't need follow-up observation, but we have the telescope at San Pedro Martyr, available to us. We can also use, maybe if we have the spectrograph at Sierra Nevada, work there, and some other telescopes. So this is something that if we are detecting those errors, we definitely go for follow-up spectroscopy observation if they were not available at that.
Right, you could also use H-beta to know how much H-alpha do you have in that plan.
Yeah, you have the extinction because we are on the extinction issues could be important.
I think we have to move on to the next speaker. So let's thank Martín.
Okay, Michaela, I'm going to give you superpowers.
Okay.
You have them now. Can you share the screen?
Yes.
Okay, and now we have to move.
I will make it full screen.
Yes, we can see your screen. Michaela, I'm gonna interrupt you when it's just 5 minutes for the time to be done, to be finished, and then once your time is gone, okay?
Okay, perfect. So, yes, I would like to explain a little bit in more detail the B supergiants that Tina and I are planning to investigate within the frame of the JALFIN project that Martín just presented. And we are mostly interested in the large-scale environments of hot massive stars. Oops. So basically, we are interested in two types of supergiants: the classical supergiants, which are found to show bow-shock structures, and the B Brackety supergiants. I will explain a little later what they are. And for those, we are interested in the large-scale ejecta. Now, when we take a look at the HR diagram, then we see that for massive stars, the post-main sequence evolution shows a variety of objects. And when you focus on the B spectral range between log TF of 4 and 4.5 roughly, you see that different types of stars overlap. So they are all in the range of B supergiants, but their nature is quite different. So we have the classical B supergiants, then we have the B Brackety supergiants, but we also have an overlap with LBVs, luminous blue variables. We do not know in detail what could be the evolutionary connection between the different states. And in addition, we do not know whether stars are in their just off the main sequence evolution or whether they have already returned from a possible red supergiant stage. So that is something, an open question, one that is very important to answer. Also, we know that some types of stars do show mass ejections, and it's not very clear what is the physical mechanism behind these mass ejections. And what is most important for us is actually to answer the question, what is the structure and evolution of the ejected material around the stars? And how does the wind or the ejected material interact with the interstellar medium? And these are the two questions we would like to address with our sub-project. Now starting with the Bow-Shock structures around B supergiants, and I show here a very nice image from the star Zeta Ophiuchi, which is a massive star, and it has been observed with the WISE satellite in different filters, where we see in the bluish mostly the normal stars, so the light from the stars, and in green, reddish, we have the emission from the dust. And we know that when stars, especially runaway stars, move through the interstellar medium with being surrounded by the stellar winds, then they can compress the interstellar medium, the gas and the dust that is available there, and can compress it and heat it. So that gives rise to very intense infrared or sometimes also radio emission. And actually these Bow-Shock structures have been found around a number of stars. They were recorded especially in the infrared, already back with IRAS, but then also in later surveys like MSX, WISE, and Spitzer Space Telescope. And these Bow-Shock structures are very important because we do know that, especially for the massive stars, when they are traveling through the medium, these massive stars have very massive winds, and the supergiants have even more massive winds. And that means that if we are able to model these structures that we observe, then we will get feedback on what is the condition in the stellar winds and what is the condition in the ambient medium. So from just the measured quantities such as the standoff distances, radii, proper motion and densities, etc., we can get very important information about these two different media. And this is shown here for one example of the B supergiant Kappa-CAS. This is from a paper of Katushkina from 2018, where they were using just the infrared images of this Bow-Shock structure in order to determine some of these parameters. But as we all know, massive stars, they have H2 regions, so they have a lot of ionized material in form of large bubbles of ionized gas. And so the idea was that these supergiant winds should also contribute to the formation of these Bow-Shocks, and they should be traceable, especially in H-alpha emission. And there has been a first investigation back in 2005 by Brown and Bowmans, who took images from the IRAS catalog and also used these low resolution H-alpha surveys, and they are mentioned here, in order to check whether Bow-Shocks are seen also in H-alpha emission. And they did find a number of stars, but they were only looking at a few runaway main sequence stars of spectral type OB, whereas our interest is more in the supergiants, because for these supergiants, the effect should be much stronger. So what we did so far is that we selected about 90 galactic B supergiants for which we know they have Bow-Shocks in the infrared, and we initiated a new H-alpha survey. And we succeeded so far already to observe 70 of the stars using different facilities in Chile, Hawaii, Australia, and our own observatory in Montreal in the Czech Republic. And we did detect faint structures in H-alpha and some bubbles in about 1/3 of all the targets. And here on the right, I show you one example. On the top image is shown the WISE image in band 3, showing a very beautiful Bow-Shock structure around one of these B supergiants. And in the bottom panel, you see one of our H-alpha observations. And you see that the structure is very, very faint. So, but the shape is similar, and we are now investigating all the physical parameters. So this is something in work in preparation. Our general goal is the characterization of the interstellar medium as well as the stellar wind parameters. And for that, we would like to combine these infrared information from the infrared together with what we can get from optical multi-wavelength imaging, not only sticking to H-alpha, but investigating as much of the emission as we can. And for this specific project here, we have identified 5 objects which are very large, of a degree scale, and they are very faint. And that means that we cannot use our facilities that we were using so far for their investigation. So we need definitely a large field of view and long exposure times. And I show you 2 examples of these large structures, and one of them has already been shown by Martín in the previous talk, which is the H-alpha bow structure around the supergiant alpha Cam. This is our H-alpha image compared to the WISE image to the right. And you see it's very, very faint, and definitely we need a much better instrument to do that. What we have used so far is our own dual 20 centimeter wide field telescope in Roncel with a large field of view, but it has a very poor spatial resolution, and it required, this top image required something like 2-hour exposure time in just one filter. So what we definitely need is deeper images with higher resolution to resolve more details of these bow structures and of the nebula. And in the lower panel, I show you an example of one of the nebula that we identified. It's also around the B supergiant star. The infrared is not very conclusive, but it seems also to have some shellish structure. But in the H-alpha, we see very nice shell around that massive star. But of course, everything requires further investigation. And coming to the B Brackety supergiants, these are some very exotic type of massive stars. They belong to the B supergiants, so they are a subclass of those, with initial masses higher than 8 solar masses. And they have, like all supergiants, they have a line-driven wind, just that this line-driven wind is much more intense than for the normal supergiants. And when we investigate these objects on small scales, some scales smaller than 100 AU around the star, we find that these objects are surrounded by circumstellar disks or a multitude of rings emitting in molecules and dust. And we still do not know the origin of these structures. But this is on small scales, and at the moment we are not looking at these small scales. But these structures are seen around all B Brackety supergiants. And for some B Brackety supergiants so far were discovered large-scale bipolar lobes or rings or arc-like structures. And the first ones have been detected in an H-alpha survey performed by Marsden and McCollum back in 2008. And well, our interest is in these objects because these structures can be very large. And I would like to show you just one example. It is MWC314. It is considered a B Brackety supergiant, but also sometimes has been referred to as a possible LBV candidate. So you see that there is some disagreement or maybe an interconnection between these different types of massive stars. But the important part is that it shows multiple lobes of ejected material. And we know that the star in the center is most likely a massive contact binary. And that means that for this object, and maybe for the others with large-scale ejecta also, binary interaction could play a very important role in triggering the mass ejections. So these stars are definitely very important objects to be investigated in more detail. And just to show that we have started already with that, using the scanning Fabry-Perot interferometer at the Russian 6-meter telescope to get information about the velocities that we were recording with the in the S2 and the sulfur lines. But we did get some information, but since everything is, the nebula is very faint, it took very long exposure times to get some first impression. So just to summarize what we are after, for the moment, we have selected 5 large and faint bow-shock nebula connected to classical B supergiants and 3 large-scale nebula around B Brackety supergiants. And for each, we need deep images, and preferentially, as Martin said already, we would like to image them in the classical or strategic nebula lines to figure out what is the ionization state in these nebula and to see the stratification. And for that, we think that JAST80 is an ideal instrument because of its large field of view. it's a good spatial resolution and the different filters that are used or offered. And these filters, although they are narrowband, they are still broad enough also to search for identifications of possible jets around these objects, because we do know that objects with bipolar lobes very often have jets. Nothing is known so far about these jets. We expect something like 10 hours per target to image each object with all necessary filters. And as I said, our goal is to unveil the physical parameters of the ISM and the stellar winds that shape the bow shocks, and also to characterize the large-scale nebula of the Bragg supergiants. And the outcome will be very important for deepening our understanding of winds and ejecta from massive stars and their interplay with the local ISM. Thank you.
All right, any question in the room for Michaela? Or in the internet? If not, I have one. You show us a follow-up with the Fabry-Perot interferometer. And I think that's, I'm curious about that. So would you need like a follow-up, like a spectroscopic follow-up of these bubbles to learn more? Or what would be the information that you will be missing if you don't have that spectroscopic information about the velocities?
Well, yes, of course, we always need to have follow-up information from spectroscopy in order to figure out what is the velocity stratification in the ejecta and in the nebula. So the Fabry-Perot is a very nice instrument, but it has also its downsides because the band is very narrow and the exposure times are horribly long. So it is one possibility for follow-up observations, but it is certainly not the most ideal one.
I see. And could you use, I don't know, some IPU instrument or something like that, or not? It's not the best for this task.
It would be ideal to use an IPU instrument, but at the moment, except for the MUSE instrument from ISO, I'm not aware of any that could do that in a reasonable amount of time, because you would have to do many pointings in order to cover really the full nebula structure. So at the moment we are really stuck, and I think the first step will be really to first get the images, to see the ionization structure, and then to decide which lines would be the most fruitful ones to do follow-up spectroscopy in order to get the kinematics and maybe the density structure.
All right. Any further questions? No. Well, if not, I have another one. So, given that with different filters, you are tracing the distribution of different components that have been expelled from the star, I guess like everything is related to some pulsation phases of the star when it's exploding. So basically, my question, because I'm completely foreigner to this matter, so could you trace back to those events and to what are the layers that are being expelled or not, or this is science fiction, what I'm talking about?
Yes, that would be very difficult. I mean, what we are doing at the same time, simultaneously, is to further develop the pulsation codes in order to see how these stars will pulsate. And we know that there are certain pulsation modes that are suitable to expel mass. And this is something that is under investigation to figure out how much mass can be ejected due to these pulsations and with which conditions, which velocities, which mass load. That then we would have to do it the other way around, that we see what the pulsations can perform, and then to see what we see in the observations and whether that can be matched. But that will be first on small scales, I guess, because until this material has then traveled out to far distances, a lot of things will happen in between that can disturb the shape and everything.
Oh, understood. Okay, so any questions? No? Well, if not, let's thank her for this.
Okay, Michaela, can you return the host status to me?
Okay, assign a new host, this one.
Okay, now, okay, now, Laurence, I give you the host permissions. So you should be able to share your screen now.
So before Laurence starts, yes, the next talk and the last one of the session is going to be Laurence Sabin, and she's going to talk about our experience searching for evolved objects with a standard emission using IPHAS.
Hey, can you hear me?
Yes.
Yeah.
Okay, perfect. Thank you. So good morning, everybody, and well, good morning for me and good afternoon for you. So I'm going to present you what we've been doing with IPHAS and how what our experience looking for evolved object and ionized extended objects. So this is also a talk linked to J-ALFIN presented by Martin. So first, I'm going to talk about the galactic plane. So we all know that the galactic plane is the site for star forming region, for massive star remnants like supernova remnants, etc. So we have a lot of extinction due to large amount of gas and dust that we have there. So if we want to do a census or any statistical study of any population, it's going to be difficult because of the initial problem to count the objects that are hidden inside that galactic plane. So let's take the case of planetary nebulae, for example. So Martin already talked about them, but just to explain, to the planetary nebulae, that are shell of ionized gas around evolved low intermediate mass stars. So we are talking about stars between 0.8 and 8 solar masses. So we know that planetary nebulae are very important for the enrichment of our galaxy, and they are short-lived, between 10,000 and 20,000 years. So what are the questions in the field of planetary nebulae? What we want to know? So first, how many planetary nebulae are currently existing in the Milky Way? So this is seems basic, but this is a viable question. Is there an abundance gradient? What are the space density, scale A, birth rate of planetary nebulae? What about the distribution, their distribution in the galaxy, their distribution maybe in terms of morphology? For example, where are all the bipolar, where are all the round planetary nebulae, etc. So if you want to do any statistical analysis, well, we need a large sample. The thing is, right now, we are limited to the bright and nearby planetary nebulae, which is normal because those are the easiest to detect. So who are the missing ones? According to Flew et al. In 2008, there should exist around 24,000 planetary nebulae in our galaxy. But if you look at the ASH catalog that Martin mentioned earlier, we have around 3,500 of them. So we are missing a lot of planetary nebulae. So who are those missing ones? So those are the ones that are hidden in the galactic plane due to actually that interstellar extinction. The old planetary nebulae that have a very low surface brightness and are difficult to detect. The planetary nebulae that are in location that are not really explored, like the anti-center. So at the outskirts of the galaxy, we don't know exactly how things are going on for the population of planetary nebulae. You have a very distant one that can be unresolved, and the one that are very compact and hidden in a crowded area of crowded stellar area, such as the galactic plane. So if we look at all the survey that have been conducted, so what we can deduce is that we need an imaging survey that is combining a large coverage and a high spatial resolution, and of course a survey that we will conduct in H-alpha, because the H-alpha will trace all those ionized nebulae, either the young one like Titori, Guerrero, H region, or the evolved one. Planetary nebulae, symbiotic stars, supernova remnant, etc. And this is when enters IPHAS. IPHAS stands for Isaac Newton Telescope Photometric H-alpha Survey. So it's a fully photometric CD survey conducted at the IMT in La Palma, which is a 2.5 meter telescope with the wide field camera with a pixel scale, which is, this is important, a pixel field of 0.33 oxygen per pixel. The area that is covered in latitude, which is the most important fact, is between -5 and 5. So it's really concentrated on the very crowded galactic plane, and actually the field which is just be scanned is around 1,800 square degrees. And the scene on site was generally around 1.1 arc-seconds. So we will have some good data. In terms of performance, what we're going to use, the filters, 3 filters, H-alpha, R, and I. The H-alpha filters contain also the N2 lines. So that's also something that we have to take into account. 120-second exposure in H-alpha. That number is important for the to keep in mind, as I'll show you why in a minute. In terms of depth, where we can go, until where we can trace those objects. So for the point source, we can go down to 19.520 magnitude, and for the extended emission, the H-alpha surface brightness, we can go down to 2 × 10⁻17 Erg centimeter square per second per arc-second square. And of course, for IPHAS, we have our own nomenclature for the compact and the extended sources. In IPHAS, we have several groups, and we are part of the IPHAS Nebulae groups. So our goal is to look for planetary nebulae, but not only, also any other ionized nebulae in the northern galactic plane. We target not only compact, but also extended nebulae using photometry and mosaicing techniques. So the photometry, it's for only the very compact or point source objects. So what has been used are 2 color diagrams, either with the IPHAS data, the IPHAS filter, but also in combination with other wavelengths. For example, the 2 mass here are example by Corradi et al. And Vironen et al., where they were looking for, Romano Corradi was looking for symbiotic stars, new symbiotic stars in IPHAS. And the mosaicing, this is what I've been working on. So we're going to target extended nebulae. So the process to do that, we've been creating 2 square degree mosaics. They are H-alpha minus R mosaics. And those mosaics were built following the different constraints that you can see on the table on the right. And the detection method is visual. So either direct, that means that we inspected visually the H-alpha minus R mosaics, or we're creating RGB mosaics. That means we're using H-alpha minus R, H-alpha, the quotient, H-alpha divided by R, and R mosaics that we combine and visually detect all those new nebulae. So we've been creating more than 1,500 mosaics that we've been looking at. An important fact is the beaming. So we use a beaming for those mosaics, 2 different types of beaming of 15 and 5 pixels. The 15 by 15 pixels mosaic are interesting because they will resolve low surface brightness objects. So we can go really down to the IPHAS limits and see all those very old low surface brightness planetary nebulae or remnant supernova, etc. The 5 by 5 pixel beaming has been used to detect the intermediate size. That means that they are too small to be detected in the 15 by 15 because they appear as stars, and they are too large or too faint for the photometry, picked by the photometry. So in order for completeness, so we use the 15 by 15 and the 5 by 5. So here, for example, it's an example of a mosaics where, and if you dig into it, well, you can see some different type of nebulosity, either known or new. Here again are some example of planetary nebulae. So you can see that this one on the left you really need some kind of, to really see those kind of objects, you really need some, to dig through all the data. And most of all, you need to have the 15 by 15 mosaics, the 15 by 15 pixel beaming mosaics are really useful to see all those kind of old pattern in the galactic plane. So after discovering all those objects, so what we've been doing is follow-up analysis. So first, of course, the spectroscopy for basic identification, but also deep imaging. So the deep imaging in the optical, which is very useful because, as I remind you, the original IPHAS data are only 120 seconds. So in 120 seconds, you do not have any, well, you do not have a lot of information either on the detail of the morphology or maybe the extent. The beaming can help you, but if you want with details, it's not going to be enough. So you really need deep imaging. We've been conducted multi-wavelength and technique analysis, one of which is the study of the central star using UVEX. So UVEX is the blue counterpart of IPHAS. So on the right, so you can see some new planetary nebulae that were observed, and those are deep image. So on the top is the necklace nebulae, and on the bottom you can see some old planetary nebulae with interaction with the interstellar medium. So they are really merging with the interstellar medium. And in blue, where you can see with UVEX, we were able to see those central stars. So here again, some images of the deep analysis and the deep imaging, so that we've started. But of course, we can do that as Martin explained, only when we have a small field of view. So we published some articles about different planetary nebulae, where we were able to see those new small structure like knots and define the ionization condition. But here, the field of view is pretty small. So if we want to see if there's something around, like halos or things like that, we need a bigger field, deep imaging, but with a bigger field of view. So we're not only analyzing planetary nebulae, we also detected supernova remnants. So here are a set of different structure that has been observed in the optical, and also we looked at the counterpart in radio. So here again, we are trying to solve the census issue, but in this time, in the case of supernova remnant, we're also working on novae. So this is one that Martin showed, which is one of the new novae that has been discovered, and all the follow-up analysis in different, for example, in X-ray that has been conducted. So in the end, what we see is that IPHAS can can detect new objects, can detect new planetary nebulae, new supernova remnant, new symbiotics, etc. But we need to combine it with another survey, another deep imaging survey, this time such as JAST, but also JPAS, in order to have some more details on the morphology. The morphology either at small scale or small scale, but to better use JAST at larger scale. In conclusions, well, IPHAS is a survey which is still unveiling several new nebulae. So we're still working on this survey. We're still exploiting the data of those surveys and this survey will help us solve the bias problem and have more to add more new objects, more new ionized nebulae to the sample of known objects. The detection of extended nebulae, we do it because we're still working on that using beam mosaics. So either with the direct detection or using the RGB technique, which is pretty efficient. We also relying on the emitters community that we're working with them on those type of detection. And for the follow-up analysis, so we are really relying on, and we really need this deep imaging. For example, if you want to do morphokinematics models, So you need a very, you need the best description as you can of your nebulae. So we hope that we will be able to do that with JAST80 in the future. Thank you very much.
All right. So thank you, Laurence, very much. Any questions? Ale? Either you said a question from there and I repeat it, or you come here.
Thanks for the beautiful talk. I was wondering if, oh, is it?
I cannot hear you now. I could hear you before and you touched something and now nothing.
Maybe now?
Yes, now I can hear you. Yeah, I can hear you now.
Thanks for the beautiful talk. I was wondering if you're looking for shells around cataclysmic variables which did not show nova explosion.
Not specifically, because what we are doing first is really looking for every type of nebulosity, and then we are trying to figure out what they can be, but not specifically. For example, the nova that have been the CV that have been showing. Well, the first classification, we put everything in the bag of planetary nebulae. So because we saw that nice structure, that nice morphologically nice structure, so we put it in the bag of planetary nebulae, and then we do subsequently we do the spectroscopic analysis and all the subsequent analysis of the central star to see how it varies, etc., etc. And then we classify it. We do the real classification of those objects. But at first, we are not going for a special type of object. We are taking everything and we do a global analysis, and then we do the classification. But that kind of object can certainly fall in our field of study. Yeah.
We keep talking about it.
Thank you.
Right. Any more questions? Please, Mohammed.
So what's the surface brightness limit? So what's the surface brightness level that's out of the nebula?
Yeah. So Mohammed. All right. So Mohammed is asking, what's the surface brightness, right? Yeah, the limit of the surface brightness in IPHAS.
Well, this is the one that I show you actually. It's around 2 times 10 to the minus 17, more or less. For the extended object, yeah.
Any other question? No? Well, if not, thanks, Lauren, again. We have to recover the superpower.
This is the last one, right?
Yeah, this is the last one.
Okay.
Laurence, can you return the host status to me?
Yes, just a minute. Okay, should be there now.
Okay. Perfect. Thank you very much.
So, thanks, please, one more time to all the speakers of the session. It is the first day of the conference. It's done. We are done. We can now have some fun or relax or anything you like. And to 8:30. So for those who are attending the dinner, I guess you have the brochure with all the information of where the restaurant is. If not, or if you prefer to go there with someone else, I plan to be at the entrance of SECA at 2020, so 10 minutes before 30, in case you want to go with us. So nothing else. Thank you, and see you in the dinner or tomorrow. I think you have it in the red backpack. Yes. Yeah, it should be in the ring. There is even a map.